Hey guys, this is 19.3 through 19.8 on the end of the chapter. And I alluded to this a little bit in the last video if you were watching it, Kirchhoff's loop rules. And it has a lot to do with how do we manage understanding the voltage and the current that flows through different components of circuits, and how do we combine all of this stuff. I mean, you look at this circuit that's here on the page, and this is a mess. It looks like a complete disaster. And yet there has to be a way to figure out how much voltage there is at each of these resistors that's being used up and how much current is flowing through them. And so what we want to do is we want to figure out how do we calculate all that. How do we figure out how much current and how much voltage there are in different locations. So Kirchhoff had two loop rules. We can see it's named after G.R. Kirchhoff from the mid-1800s, and he had two rules that had to do with energy and with charge. If you think about current as the flow of charge, or similar to a flow of a river, you can't, when you have a fork in the river, you're not going to suddenly have more water flowing or even less water flowing than you started with. The water's going to continue to flow down those canals or through those junctions. So similarly, he said in his first rule, it's the junction rule, he says, okay, if this is I3 right through here, and it splits into I1 and I2, then we could say that I3 must be the sum of I1 plus I2. The Kirchhoff's junction rule, or Kirchhoff's first rule, tells us that any junction, the amount of current that goes into that junction must be the amount of current that comes out of that junction. No current is gained or lost. That also tells me right now that, man, I1 and I2 probably aren't as big as I3. Now, the truth is, we don't know. Maybe I1, this current, is the original current. Maybe it splits into I2 and I3. So depending on which one is going in which direction, it makes a difference. I just used the arrows that they had shown in the diagram. You can see they said I3 splits into I1 and I2 based on the arrows. If we have the arrows labeled wrong, this problem will have a negative in it somewhere, and we'll figure that out. But the problem with this is three different variables, I1, I2, and I3. And we can't possibly solve for all of them unless we know two of them. Well, Kirchhoff's second rule is called the loop rule, okay? And it says that through any closed loop, meaning you started in a place and you made it all the way back to where you were, where you started. So if I take this loop, say right here, and I go all the way around, back to point D, if I make a closed loop, my total voltages has to equal 0. Okay? And so if we look at, say, this loop right here, all right, we know we've got a 45 volt battery. So I've got 45 volts. Okay? But I'm going to lose some voltage right here in my first resistor. Well, how much voltage do I lose? Well, Ohm's law says the voltage equals the current times the resistance. So I'm going to use I times R for my current and resistance to get my voltage. So I'm going to lose, or minus, 1 ohm times the current, which in this problem is labeled I3. So that'd be I3 times 1 ohm for the resistance. I'm also going to lose some voltage here at the 40, so that'd be minus I3 again times 40. And as I turn the corner, now I'm dealing with I2. See that? And I no longer have I1, but I do have another battery. And this second battery would, because I'm going in the same direction, from negative to positive, this is the right direction for the current flow, that would be a plus 80 more volts. I'm going to add 80 more volts because of the battery. And then over here I have another resistor, so I'm going to minus the current I2 times the resistor of 1. Now when I simplify all this up, you'll notice that I3 and I2 show up in this equation. So I now have two equations, right? I have this equation up here, I have this equation up here that reference I1, I2, and I3. Now the second one is a little simpler because it doesn't have I1, but it's fine. If we created one more equation, we would have a 3 by 3 system of equations. And we learned back in Algebra 2, and I know again in college algebra or pre-calculus, how to solve a 3 by 3 system. We'll go over that in class, but suffice it to say it's the, x plus y plus z equals, 1, 2x minus 3y plus 4z equals 8, and so on, where we have 3 different lines. If you're struggling with that, look at the solutions or come in and let's have a conversation about how to do that algebra. The assumption is that you've got a basic understanding and you can move forward from there. But if you have more questions, I'm happy to go through those with you. But Kirchhoff's loop rules allow us to do all of our solving for current, and once we know the current, we can find the voltage at any of these points. A couple things to keep in mind. If you go backwards, across a battery, like say that I was going this direction, if I had said I'm going to do that loop, for instance, you might take I1 around and go around the big loop, but that would mean I was going backwards against the battery, so that would be a negative 80 if I'm going backwards across the battery. And anytime your I says go one way but you're going the other way, that's fine. But every time I cross a resistor, instead of subtracting voltage, I'm going to have to add voltage. I have to be consistent about my current. If I say current goes clockwise, but I'm going counterclockwise, I have to account for that. So signs do matter a lot here, so be very careful to make sure that you work on it that way. All right. So Kirchhoff's loop rule is convenient because if I had to build the total resistance for this circuit and the total voltage, it might be a little complicated to get all of that done. And so this gives me a convenient option. Now, there are a couple of things still that we need to talk about in terms of working on circuits that have loops in them and multiple paths. We talked a little bit about it last time, but I'm just going to address it again here. A couple of rules that you have to understand. All right. In any circuit, if you have a series connection, in series, the current is constant. So series means that I is constant. Through any series connection, the current's not going to change. In parallel, it will split, and so that becomes difficult to work with. But the good news is, because of Kirchhoff's loop rule, if you can imagine, I've got 2 different resistors down here in parallel. Because of Kirchhoff's loop rule that says whichever path you take, you have to use all the voltage. You're cruising through here. If you take the left path, say that this is 9 volts, and I use 4 volts here, this guy right here would have to use 5 volts. But if instead I chose to take the right path, I would still have to use 5 volts. So in a parallel path, the voltage across any parallel component is held the same. So parallel, V is constant. Now it's just just across those parallel components, but the voltage is constant. That's going to help us solve a lot of problems that way. All right, let's go ahead and talk about our last couple of rules. These are pretty easy to work with. If you've understood the resistance from last time, how you add resistors in parallel and series, we're going to have a very similar approach to our next section. Here we go. Come down here. There we go. We got capacitors added in parallel and capacitors added in series. Well, remember that capacitors are all about piling up charge. You can imagine I'm pushing all these positives in. Whoops. Let me get back off of there. I lost everything. Whoops. Let me try erase a little technical glitch here. See if I can get it to come back. All right. There we go. So if you look at it here, when we have the capacitors in parallel, charge can build up on every single one of these, right? So I can go down here, I can go through here, I can go up here. That maximizes my capacitance. I'm going to be able to put up a lot of charge stored on these capacitors. So I know that in parallel, resistors added with that 1 over R plus 1 over R plus 1 over R, but when capacitors are in parallel, they add as just C1 plus C2 plus C3 and so on, as many capacitors as you have in parallel. Coincidentally, when you add capacitors in series, okay, you end up with the fact that one capacitor stops flow to the other capacitor. They're impacting each other when they're in a line. All right, if this capacitor is connected to this capacitor, connected to this capacitor, well, guys, the amount of positive charge I can build up on this plate is going to affect the amount of charge I can build up on this plate because I can only push so much. And so they negatively impact each other. And that means that we're going to get less capacitance out of the circuit. Now, sometimes we don't want much capacitance for one reason or another, but anytime we put them in series like this, this is when we end up with the 1 over C1 plus 1 over C2 plus, and we do that as many times as we need to, all to the negative 1. So capacitors and resistors add in exactly the opposite way from one another. Series versus parallel, they're exactly the opposite. So hopefully that helps you understand why we're using that. But different formula for different components. All right, so let's keep rolling. Last thing you need to know about, it's real simple. There's some stuff in here. RC circuits, resistor capacitor circuits, they have a time constant for reloading. This is why they work well in clocks, because if you set the reset time to 1 second, it can discharge and reload every second. You can have a really good timepiece. You can, for instance, like with a pacemaker, something that's going to keep the heart in rhythm. Really important that you have it set at a specific rate. Of course, there are electrical hazards. I'm not going to worry too much about them. I think you guys know not to stick a fork in the outlet or in your toaster. But there's a couple things that you need to understand about measuring voltage and measuring current in a circuit. And there's really only one thing I want to talk about. It has to do with how you hook up a voltage meter or an ammeter to measure current and voltage. Okay, if I wanted to measure the voltage across a resistor, I can just plug in anywhere into the circuit and create a new path. And this new path is where I'd put my voltmeter, okay? And this would tell me the voltage here and the voltage here and give me the difference. Because we know voltage is held constant at parallel paths, okay, this parallel path would have the exact same voltage drop that the resistor does at R1. I can do the same thing for R2. Current, though, the problem with current is when you create a parallel path, if I tried to put an ammeter here to figure out the current that flows through there, if I put an A there, the problem is when current hits a junction, it splits into two different paths. I don't want the current to split. I want the current to be the same thing that flows through R1 naturally. So I have to put that ammeter somewhere else along the line. You can see they drew it down here. But the key is it has to be in series with what you're trying to measure the current through. So that's really important when we try to make measurements. That means that in a circuit, it's easy to measure the voltage between 2 points without taking it all apart. But with a current, if you want to measure the current, there has to be a break in the circuit in order for you to insert that current meter. Okay? And there are places that we can naturally do that, but otherwise we might have to cut a wire or break a component off and replace it. So those are things that we have to think about when we're trying to measure current and voltage. Voltage can be measured parallel, but current has to be measured in series. And that has to do with what I said earlier about the fact that voltage is held constant across parallel lines, current is held constant in series. All right, good luck, guys. You're going to have questions. Just come in and let's talk about them. All right, we'll see you.